AI is quietly moving from generate and hope towards systems that can decide when to reason, how to reason, and whether control will even work before the full output is finished. That matters because it turns reasoning and steering from black box tricks into optimizable, testable mechanisms, which is exactly what you need if you're building reliable agents or trying to scale inference efficiently. The common thread here is control, latent recurrence that can be trained with RL, diffusion models that stay bidirectional all the way through, and predictors that estimate steerability from the first few tokens. We'll unpack why those shifts are more than benchmark wins. Let's explore the first paper, Demystifying Hidden State Recurrence Switchable Latent Reasoning with On-Policy Reinforcement Learning. This paper from HKUST-GZ, the University of Cambridge, and NTU introduces Switch, a switchable latent reasoning framework for Qwen 3.8b that makes hidden state recurrence compatible with on-policy reinforcement learning by adding explicit is less than SWI is greater than and is less than SWI is greater than boundary tokens around latent blocks. The key technical move is that GRPO is applied only at discrete text positions, while latent positions are replayed through deterministic hidden state injection, so the policy ratio remains well defined during training. Switch is trained in 3 phases: supervised tagging of high entropy reasoning spans, a curriculum that progressively replaces text with is less than latent is greater than steps, and a switch GRPO objective with correctness, format, latent usage, and optional brevity rewards. On Math 500, the full system reaches 79.3% accuracy, beating the strongest Coconut-style hidden state recurrence baseline by 25.7 points at the same Qwen 3.8b scale, and on GSM 8K, it reaches 89.2%. Relative to the curriculum-only checkpoint, Switch GRPO raises latent conditional accuracy by 12.6 points, while cutting switch usage from 81% to 58%. Mechanistic analysis shows that is less than SWI is greater than is a sharply localized learned control token. Probe accuracy for predicting the switch decision reaches 91.9% at the last layer, and causal interventions confirm that the injected latent state is functionally necessary. Zeroing, it drops diagnostic accuracy from 100% to 33.3%, whereas a same norm random vector is far less harmful. The authors conclude that hidden state recurrence is both RL trainable and directly interpretable. Let's explore the second paper, Improved Large Language Diffusion Models. Improved Large Language Diffusion Models introduces ILLLDA, an 8B fully bidirectional mass diffusion language model trained from scratch at ByteDance Seed with Renmin University of China. The paper keeps the mass diffusion objective throughout pre-training and supervised fine-tuning, but scales pre-training to 12 T tokens, fine-tunes on a 2.5b token instruction corpus for 12 epochs, and adds grouped query attention, tied embeddings, variable length generation, and confidence-based scoring for multiple choice evaluation. These changes substantially lift performance over LLADA. The base model gains 21.6 points on BBH and 14.9 on Arc Challenge, while the instruction tune model gains 14.5 on math and 16.5 on human evil. On the base suite, iLadder reaches 74.8 on MMLU, 81.9 on GSM 8K, and 50 on human evil. And on the instruction suite, it reaches 89 on GSM 8K, 56.7 on math, and 65.9 on human evil. The ablation shows confidence-based scoring improves multiple choice accuracy by 1.3 on Piqua, 0.6 on Arc Challenge, and 2.3 on HellaSwag versus likelihood scoring. Overall, the study argues that fully bidirectional diffusion training from scratch can be competitive with strong autoregressive models such as Qwen 2.5.7b on several reasoning benchmarks. Let's explore the third paper. When is your LLM steerable? This paper from the University of Maryland and MBZ-UAI asks a precise question. When is an LLM steerable? And can that be predicted before a full generation finishes? The authors build aSteer, a large testbed of 142M, labeled steered generations, covering 150 concepts, 50 prompts, 3 LLMs, and 2 steering methods, diffmean and probe, with outcomes annotated into understeer, sooksteer, and oversteer using GPT-5. Nano and validated against human judgment with Cohen's kappa of 0.83. They then propose SteerBoost, a gradient boosting decision trees classifier that reads only the first few decoded tokens and compares steered versus unsteered hidden states across a token layer grid using interpretable geometry and decoding dynamics features such as steering affinity and deviation alignment. On held out unseen concepts, steer boost reaches around 0.7 macro F1, with diff mean performing strongest at about 0.8 on in-distribution concepts and about 0.72 out of distribution, while probe is harder to predict at roughly 0.68 to 0.74 ID and 0.65 to 0.69 OOD. The model shows that the first two decoded tokens carry over 75% of the feature importance mass, and it enables steering strength search that recovers about 98% of item-level oracle success, while using only about 11% of the decoded tokens required by exhaustive grid search, making steerability prediction a practical shortcut for cheaper, near-optimal activation steering. That's a wrap on today's AI paper highlights. Thanks for watching.